All right, this is a review section for exam 3. Exam 3 cover chapter 8 and 9 and 10. I'm just going to go through some of the practice problem and give you some heads up about the topics that is important to these 3 chapters. So let me share my screen to show the notes. Exam 3. So the study guide that you can find from Canvas, so it's under week 13, I believe, and then you click on the review study guide, the exam study guide, that you will see a page with some of the topics and also some practice problem here. So I'm gonna just go through each of these and tell you some of the thing about the 3 chapters. The first chapter, the chapter A, is about the value. It's about the fractal. So things fails, then they start with 2 different kind of a value. One is the ductile, one is like brittle. But most of the time, there's some value which is in between. So we talk about the brittle and ductile to be more like extreme case, but there's something in between as well. The first problem over here, they talk about a component of the airplane they fabricate with the aluminum foil, the aluminum alloy. I have to restart my notes because it doesn't allow me to write. So let me restart. So the alloy they are going to use have some specs, and the spec is they tell you this plane strain fractal toughness. Okay, so the toughness is kind of represent how much energy the material can absorb during the service. And they give you this number, then you need to know what is the definition of the plane strain fractal toughness. That is the K1C. So in this chapter, they talk about several different K, and you don't want to mess up with the K. So you need to know the definition for each one of the K. And this one particular one is the one that you assume the thickness of the component is not going to affect how things will fail because of some internal defects. This internal defects will create the correct propagation, which will make things fail. So that is the thing that you have to know how to do this kind of calculation. Let me bring the let me write down those equations over here that we can. By the way, there's a formula sheet that I posted already that you wanted to download and write some notes. That you can write notes. Just don't know like a workout problem, then it'll be fine. Then you can write the notes and write down this what the symbol means. Okay, so there is a KC, there's a K1C. Okay, this I here represent 1. The KC is the fractal toughness. And the K1C is the plane fractal toughness. Their unit is MPa and square root of M. So that's the unit for these 2. And you got this number, then let's look at what this equation looks like. This is equation 8.5. This KIC to the K1C is equal to Y times sigma and square root of a pi times A. This one is a constant. It's not yield stress. It's not Young's modulus. So don't mess up this one with the so Young's modulus or etc. etc. This is just a constant. Okay, so it's a constant depends on the situation and depends on the material that you're using. The sigma here represent the applied stress. Or the surface stress. This one represent the size of the crack. Okay, the size of the crack. Now, when we talk about the size of the crack, then you have to know it's internal or is external. If that is internal, then you have to divide by 2. So that's another thing that's important. Maybe a lot of people make mistake was didn't pay attention to the size of the crack. So when you have the size of the crack, it's inside. This is 2A. If you have the crack on the surface, and this is A. Okay, so what kind of a crack did they give you? They give you an internal crack size. Okay, so that means this is a 2A. Okay, that is 2A. So we got 2A is equal to 8.6 times 10 to the negative 3 meter. That is the things that given to you. What else do they give you? They give you if you have a stress 112 megapascal, the maximum the internal crack size is 8.6 times 10 to the negative 3. So they tell you this sigma is equal to 112 megapascal. With this information, you can actually do the calculation of this problem because the K1C they give you is 26 megapascal square root of meter. And then everything is given but the Y. So the first thing you do is actually to find a Y. Okay, so the Y will be equal to your K1C divided by sigma divided by square root of a pi times A. And you got all these numbers that you put in, then you can get the result. So this is, I don't have the, I didn't calculate this. Let me just quickly find the result. This is a 112 times the square root of pi times A is going to be 4.3 times 10 to the negative 3. Okay, so that is the thing that you need to find. And I'm doing a quick calculation to find out what the answer is. Okay, so I got this Y is approximately equal to 2. So that is 2, then what you have to do is that they wanted you to find what happened if the internal crack size is 6. It was 8.6, but now that's changed to 6. Okay. Okay, so what happened if this one changed to this? And then you can use the same equation, but now Y is given, well, we just determined the Y, so your KIC is still going to be the same. That's the spec of the material. And Y is 2. Then sigma is the thing we try to find. The pi is still a pi, a constant. The A now is become 3 times 10 to the negative 3. And that is the A that you use at here. So your sigma is going to be 26 divided by megapascal divided by 2 and divide by square root of pi times 3 times 10 to the negative 3. And that is your result. So let's do a quick calculation. Okay, so I got 134. So that result turns out to be 134. So that's how you do this kind of calculation. You can certainly ask a different question. We can also ask you the size of the crack, or we can change the crack to be on the surface instead of the internal one. And there are three different kind of the fractal toughness as well. So the type 1 is the one that we have the most. It's the stress is actually trying to take it apart. Okay, is that you give the stress in this direction, then this is the type 1. Okay, so this is the first problem that we're looking at. The chapter A also look at the two different kind of spatial value. One special value is called the fatigue. So this is the fatigue problem. Another type of the value is the creep. So the creep is that you put the material at some kind of a load at a certain temperature for a long period of time. And then the material will start to creep with a creep rate. Then we do a lot of practice doing the homework that you have to know how to find those constants. It depends on the temperature. It depends on the energy of the creep, the activation energy for creep. It also depends on the time and also the stress that you apply. So that is, let me write it down for the creep. This is the creep rate, which is this one here, and this is equal to some K2 sigma n and exponential of a minus QC over RT. Okay, so that's the creep. Okay, so I'm going to just look at the fatigue. So fatigue is that you give the load, a periodic load, and you give that uh, for many, many times, okay? And then we look at how long will the material last if you give this kind of loading condition. Most of this graph are using the log scale for the time. This also works for the chapter 10 when you look at the heat treatment. At the x-axis, we also use the log scale. So this is the good practice that you know how to read a log scale. I also put a scale on this notes that you can see. If you look at the linear scale, then everything is like evenly spaced, right? So these spaces are all equal. But the log scale, they are not like an evenly distributed space. 1 to 2 is about 1/3 of the whole length. 1 to 3 point something is about half, right? So 1.3 is almost like a half. 1.2 is about like 1.3 in the linear scale. So when you read this, you have to be careful how you read this. Okay, so how do we find this? Well, you were given with a rotational velocity. So what does the rotational velocity tell you? It tells you 600 RP, and that means you give the load for a minute, in a minute for 600 times. So it's a 600 cycle per minute. So this one tells you you're given with 600 cycle per minute. Okay, and they also give you two different stress level. That's the stress that you apply to the material. The first one is 450. So 450. Then the way that we read this graph is that we draw a line along the 450 line here. So the 450 is marked on this graph, so you can draw the line. So 450, we just draw the line from the left to the right. It will intercept with the curve. The SN curve give you an interception. So this interception that we draw vertically to find this value. Well, you can extend this one to the bottom because this one I give you a scale. So you can see this one here. It's not like 10 to the fourth. It's more than 10 to the fourth, but how much more? Well, the first one, this one here is 1 times 10 to the fourth. This one here represent 2 times 10 to the fourth. So this point simply represent 2 times 10 to the fourth. It's not 4.2. Don't make it 4.2 times 10 to the something. So this is representing as 2 times 10 to the fourth. So we know that 450 megapascal, the log life is 4.2 times 10 to the fourth. That is cycles. And we want to find the life, meaning we need to find a time. And how do you find a time? To find a time, it's equal to your total number of the cycles, and you divide by the RPM, because the RPM is cycles per minute. So when you divide these two, then you got the time, which is in minutes. Okay, so this one here is 4.2 times 10 to the fourth, divide by 600, and that give you the minutes. And that is going to be the result in minutes. So I got this one. Oh, wait, I was right. Yeah, that's right. So 2 to the power of 4. No, that's 2 times 10 to the fourth. I was wondering why I write this. So it's 2, it's not 4.2. It's 2, so 2 times 10 to the fourth. And divide by 600. And you got 33.3. So that's when you apply 450. The second case is 275. So 275 is just right below this line here. Okay, what does that mean? If you apply the low, which is right below that line, which is the life of the limit of the SN curve, that means it's going to have an infinite life. So that's how you do this SN curve problem. Okay, the number 3 problem is asking you some They give you a picture. It shows you what kind of asking what kind of a value this is a brittle or this is a ductile. So I summarize a table over here to compare the two different fractals. So if you look at the ductile, it's on the middle column. The brittle is on the right hand side. And we can look at how much strain energy required. So if you look at the strain energy, you can look at their stress and strain curve. So this is our stress, this is our strain. If the material is brittle, then the brittle one will give you this kind of value. If a material is ductile, then the ductile will go like this. So this is the ductile and this is the brittle. The brittle, well, if you look at the strain energy simply represent how much area under this, right? So which one has a larger area? Well, the ductile has a larger area. And just based on the area, you can tell which one is higher, which one's lower. And the stress, the brittle has the stronger stress, and normally it's going to be the fractal is going to be constant. And when you have the crack, then the value, the stress will still increase, but the brittle just break at the time. And there's a crack propagation. When you have the brittle, that means the propagation is very fast. That's why it fails so fast. Um, Warning sign, the ductile, we like ductile because it's plastic deformation. It gives us the warning sign. So the ductile give us the warning sign, but not the brittle one. Deformation, obviously, ductile have more of the deformation than the brittle. And knacking, meaning the material will start like the same thickness. Then once it start to elongate, it will start to form a necking in the middle of the material. And this is what you did in the lab, right? So this is what we call the necking. The brittle doesn't have a necking. If the brittle fell, it will feel like this. Let me use different color. So the brittle one will feel like this, like a flat surface. But the blue one, which is ductile, they will have a necking, and when they fail, they're actually going to have a narrower, uh, the narrower region in the breaking surface. Okay, and that pretty much is the difference of these two. Now, there's certain pattern that associate with the fail. The most famous one is the V shape, or the shaft long marking. That is the brittle one. So the picture that you see on canvas, that one is the shaft long marking. You can see the V shape, and sometimes they will have like a delta shape, and that kind of tells us that is the brittle one. The next one is about the phase diagram. The phase diagram has a lot of information. The first one over here just ask you some sample of the point that you should identify. The particular phase diagram that we give to you is the tin and the gold. So you have two different materials. This is a binary phase diagram, but as you can see, the phase diagram is so complicated. It is complicated because for this system, you have some intermetallic compound. So all this here represent intermetallic compound. The intermetallic compound will be a composition of the gold and also the tin, uh, and it has a different number of the more. For example, if you look at this one here, the first one that will show it here maybe is the um, one goal, sorry, goal should be AU. One more of the goal is going to combine with one more of the team. And the second one is that you're going to have more of the gold and less of the tin. So when you combine them, then this will have two parts of the gold with one part of the tin. Okay. So it'll be similar like this. You have to actually do some composition calculation in order to figure out which one is the one more and which one is the two more. This number might not be right. I'm just kind of a guess that probably is this. Then the next thing you need to know is that, okay, there's so many solid solution in this picture. All these alpha, beta, gamma, delta, and eta, those are all solid solutions. So alpha, beta, gamma, and delta, and eta, they are solid solutions. Okay, and the solid solution, the alpha is going to be the composition with more of the tin. Okay, and the beta is going to have more of, if this one is the intermetallic compound, it will have more of this. Okay, etc., etc. That you can see there's a lot more. There's another one here, actually, eta. So there are a lot more of the solid solution in here. This here is the largest region, which is the liquid, meaning the temperature at a certain position composition. Then you can find when at what temperature they will become a liquid. Now we want you to specify what we want to specify temperature and the composition point at which you have a eutectic, eutectoid, and peritectics. Now, to find those things, you need to know what are the eutectics and what are the eutectoid, what's the difference between them. So over here, I find a picture to show you what are the difference. There's a reaction equation you can find from the textbook. So if you have a eutectic, which is this one here, it's liquid to two solid states, so two solid solution. So this point here is the point that you're going to have a eutectic, and that is the point that that represent the eutectic. The eutectoid is this one here, which is one solid to two different solid. The peritectic is the liquid and the one solid state to another solid state, which is this point right here. Okay, so these are the things that you need to know. Well, the other one is peritectoid. We didn't do this one in our book, but that is the one that you have one solid state to two different solid state. Okay, so that is the different of the reaction, and let's look at the how we find those things in here. So you basically you find where the intercepting point where you have three different states is there's three phase reactions. Okay, so either is a combination of liquid and two solid solution, or the liquid to two solid solution, or one solid solution to two solid solutions. That's the uh, situation. Now let me use different color to represent that. Let me just first use the black color to represent the eutectic. So in this picture, the eutectic is the liquid to two solid state. So here is the one of the eutectic. Okay. And do we have more eutectic? Well, looks like this one is also a eutectic. Okay, so we have two eutectic. To find the temperature, you go to the y-axis, you can find the temperature. The composition is that you look down here, that you got the composition, right? So you should know how to read those things. So the black one represent eutectic. The eutectoid, and let's look at the eutectoid. What's the eutectoid? It's one solid solution to two solid solutions. So do we have a one goes to two in this case? Um, Maybe it's a good idea that we write down all this reaction first. Some of the phases are here. This region is the liquid plus alpha. This region is alpha plus beta. This is the beta plus gamma, gamma plus delta. This is the uh, liquid plus beta, and this one is the liquid plus delta. This is the liquid plus this liquid plus gamma, liquid plus delta. This is liquid plus eta. So these are the things that you have, and oh wait, liquid plus alpha. Yep. Um, all right. So do we have a situation that you have a eutectoid that we look at? Are there a solid solution become two different solid solution? I'm trying to see if I make any mistake here. This is liquid plus beta. Yes, liquid plus this one here. Okay. All right, so let's see we have any of the solid to solid in this case. If we, I so far I don't see any of those at here. Let's see. So looks like I don't see any of these things happening here. Um, let's look at the peritactics to see if we have that one or not. So peritactic is the liquid plus one solid to another solid. So liquid plus solid. So we have a lot of the liquid plus solid, right? Like like this one here, this one here. These are all the liquid plus the solid, and it will become a solid solution at the bottom. So it then, if you wanted to identify that, then you see if there is a point. So this here, let me use different color to represent that. Let's use, oh, we use the blue. So here you have a liquid plus the a solid solution into another solid solution, which is the beta, right? Over here, you also have um, this one here, which is the liquid plus delta, and become n gamma. So these two are the solid solution with the liquid plus solid solution. Okay, so these two are the eutectoid of reaction happen in, well, is that? No, that's the peritectic. This are the peritectic. Let me modify this one here. Okay, the congruent point is the point that you go directly from the solid intermetallic compound goes to the liquid, which are some of the peak points in this graph. So the congruent point is this one right here. So this is the congruent point. And the composition at that point is some intermetallic compound. Um, Again, you have to do some calculation in order to know what kind of compound that is. Let's see what else. Do we miss anything here? Okay, and all right. So to find the temperature, you go horizontally and you find the temperature, and you can define where the temperature is going to be.
So what about the hypo and hyper eutectic and eutectoid?
Okay, yeah, that's the next one question. You look at the question, they say determine a state at a 200 degrees Celsius and a composition of 70% to 30%, right? So let's find where that point is. So 70% of the goal. So here is 100% of the goal. This is 0% of the goal. So 70% of the goal is around here, right? This is the point that you start with the composition. 30% of the thing, so 70% of the goal. And you look at the temperature of 200 degrees Celsius. So 200 is at here. So this is the point that you look at. So what will be the composition of this point?
That'd be the eta plus the delta.
Yeah, it's the delta plus the eta here. Okay, so you can see this line here is this, and this is the composition on the right hand side. So it's the two solid solution of the delta plus the eta. So there's like two phases. Now this is a eutectic, right? And if you look at the book, if the composition that has more of the concentration beyond the eutectic, which is toward to the right, this region is called a hyper, and this region is called a hypo. It is determined by the composition of the tin. So if the tin composition is less than eutectic, it's a hypo. If it's more, is the hyper. So in this case, it's actually on the left-hand side, this one will be the hypo. So this will be the hypo, not a hypoeutectoid, but a hypoeutectic. Okay, because this is a eutectic equation. Okay, it's the eutectic point. So it would be hypoeutectic. Okay, any question about this? We can ask more question just from the face diagram. I haven't talked about like the level rule. You've been doing a lot of level rule in your homework. So let's say if we look at this, if we look at the composition, which is the 70, 30 at the 200 degrees Celsius, then we can find the wave fraction of delta and the eta. So what is the wave fraction of this and what is the wave fraction of this? And you use the level rule. So we're looking at this region right here. We need to get several composition point first. So one of the composition point is this composition point. This point, it's about 62. Okay, 62% of the gold. Um, this is the starting composition that we have. This is the C0 in your textbook. That C0 is 70%. And the other one is the composition at the very right end. This one here is 90%. Okay. And the level rule is that you separate this into two segments. So this one, let's say this is an X and this is the Y. Then the level rule give you this way to find the composition. The bottom part is going to be X plus Y. And the top one will be the other side of the length. So you want to find delta, you're going to use Y. And for eta, you're going to use the X. Okay. Now, what is the length of Y? Well, the length of Y is 90 minus 70, that's 20. The bottom part is the total length, that will be 90 minus 62. And this one is going to be 70 minus 62. The bottom still 90 minus 62. And you multiply with 100, then you can get the percentage. Okay, so if you do the calculation, this one turns out to be 71.4, and this will be 28.6%. Okay, so that is what we have in here. Okay, let's look at the well, one more thing about the phase diagram is that you also need to know like a microstructure, and we are not going to ask you this kind of a microstructure. This is too complicated, but at least you need to know the iron carbon one. The iron carbon one is the one that we spend most of the time to study. So make sure that you know like the ferrite, peroeutectoid, and cementite, how they are composed with each other, how they have the layered structure in the pearlite. So look at that, look at the book, and then you understand what the microstructure looks like. The following one is about the TTT diagram, which will look at the kinematics of the transformation, and this is related to the heat treatment. You have a lot of homework asking you about if you have a TTT diagram, how do you find the certain composition of certain kind of a end product of the material. And we put most emphasis on the iron and carbon steel. So this is a carbon steel composition. The A represent austenite, which is the gamma. The P represent pearlite. The B represent the bainite. And the N represent the martenite. Martensite. Okay. The pearlite, they also separate into two regions. So you actually have a coarse pearlite and the fine pearlite. So there's a region to distinguish these two. And that just simply to represent how the layers thickness is. The coarse one is going to have thicker layer, but the fine one will have a thinner layer. Okay, so here they just give you one example. They want you to find how do you draw a line to represent that you're going to produce a steel with a 50% martensite, 50% austenite. Okay, now 50% martensite, you can see it on this diagram, which is this one here. If this is a 50% martensite, then what is the other 50%? Well, you can see they can't tell you the other 50% is the austenite. So if you wanted to get this product, then you have to make your end process to be end at this line here. So to get this, then it's very easy that you start with some temperature above the eutectoid temperature. This temperature here is I think 727, something like that. And then you're gonna start, let's say you start from here. This may be like 750 degrees Celsius. And how do you get to the 50%? You're gonna rapidly cool the material to this temperature. And you're going to hold this temperature. So you are going to get 50% of the martenite and 50% of the austenite. A lot of questions that we ask you in the homework that will say, oh, then quench to the room temperature. We don't quench this. If you quench this, then everything will become a martenite. Okay. So in this question, you don't quench. If you quench, will be 100% martenite. So the answer for this one here is going to be stars. And then you're going to rapidly cool to what? To this temperature here. So this temperature, I would say, is about like a 260. Oh, not what 260. This is 160. And this 160 degree is the end 50% line there. Okay. You're going to hold it at that same temperature. Okay. This will give you 50% of the martensite and 50% of the austenite, or the A. Let me write A. If you do this, if you quench this, then you are going to get 100% of the martenite. Okay, so if we ask you this, then you are going to stop at 160 degrees Celsius. That's how you get this product. Let's do maybe like one more example, and then we will go look at the last question. So let's say if you wanted to create 100% of the fine pearlite. Okay, and then how do you find this one here? Let me use different colors. So, okay. So again, you start with the high temperature. And where's the fine pearlite? Fine pearlite is in this region. So you have to lower, rapidly cool to the temperature that is not reached to this north, but is very close to that region. And then you're going to hold it for a certain amount of time. Once the time go over this 100% line, which is this line over here, then you are fine. Okay, so let's just say if I go over to here, and then you have to do a quench. Okay, so the green one will be the one that you can create 100% of the perlite. So again, you start from 750 degrees Celsius and rapid cool to, this will be probably like a 570, and hold for how much time? It's about 10 to the second. That would be 100 seconds. And then quench. Quench to room temperature. So that is the process if you wanted to create 100% of the fine pearlite. Okay, so you got a lot more practice in the homework. So make sure that you go through those and understand how you use different process to generate different product in this way. Okay, so that is the answer for this problem here. Okay, let's look at the last one here, which is a design problem. So over here, they give you an eutectoid steel, and they use the continuous cooling heat treatment, which is kind of a CCT problem, and they wanted to find, well, if you wanted to generate an alloy with 260 of the hardness, Bernal hardness, and 20% of the reduction area, which is the ductility, then how are you going to do this heat treatment in order to get this product? Okay, so so the first thing you do is to actually find out what is the composition of the carbon if you wanted to generate this kind of a material. And they give you two graphs. On the left hand side, you have a hardness graph with the percentage of the composition of the carbon. So that's use this the first one to find what we have. So hardness number is 260, which is around here. And you draw a horizontal line, and you will see the only way that give you this is that you have to get the fine pearlite. Okay, the fine pearlite. If you wanted to generate fine pearlite, and what is the amount of composition, then you go straight down, you can find this composition, and here is about 0.7, maybe like 3. Okay, and then you look at the right hand side, if you have a 0.73, and the 773 is about here, and you go straight up, And then you look at the ductility requirement, which is 20%. Okay, so 20% is here. It also tells you that you need to get like something close to the perlite. So you basically need to find how you can generate a perlite and at that composition, right? Um, so then they probably will give you another graph. Then you can use the TTT diagram, which is this one here that we have, if you wanted to generate that kind of a components, right? So how are you going to do it? Then it's basically that you need to generate the fine perlite. And you look at the graph, then you can start with 750. And then you are going to do the cooling to the region, which is the higher temperature above the north. And it will be similar to like a 570 that we just described to you. And you're going to hold it for a long period of time. And then you're going to quench it so you can create the perlite in this way. Okay. So this is how we can actually create these things. And here, any question about this problem? So this is the one that we did.
So if this is like an exam question, you just want us to draw the points on the graphs and that'll be good, or do you want us to like explain it in words as well?
There is, yeah, you kind of explain that. Actually, there's another graph I didn't attach it here. There's another graph that shows you the rate, because the different rate of cooling, it will give you a different product as well. So let me find what that graph is. So there's a graph like 10.28 and 10.29. 10.28 is for the carbon steel. 10.29 is 4340 steel. So we need to find the rate of cooling
Okay.
that will generate this kind of product. Okay. If that is 4340, then you use the figure 10.29.
Okay.
Okay. So this is about what I wanted to say. I didn't talk about the tempered martensite, but you should know the tempered martensite is that once you get a martensite, it's too brittle. It has less use, then we normally will reheat it to a higher temperature. So the martensite will have a better structure and better property, and which is going to be a tempered martensite. So that one you have to increase the temperature to be in a range. Okay, you cannot create to be too high, cannot be like too, well, if it's too low, it's not going to transfer. It's not going to transfer into the tempered martensite. So that is the tempered martensite, how you can create that.
All right.
Okay, so that is it. And so on Thursday, I will answer questions. If you guys have questions about like homework or about the exam, then I will give you some like a hint or help you to get that.
Okay, I'll bring some questions for you on Thursday. How long until this video is posted?
It will in probably like 30 minutes.
Oh, cool.